So here we have the basic structure for the module called one wire receive. It has some parameters, so I call this a parameterized module since we can change these parameters from outside the module. Okay, so here I specify the number of sync bits and the number of data bits, my default values. Then I declare I make even some local parameter calculations here, and then I declare my inputs. And in the newer standard, the Verilog, there's a Verilog 1995 standard, there's a newer 2001 standard, and in the newer standard you're allowed to go ahead and just put the wires or regs right here on the same line as the input and output. Typically before you would put them separately, you'd just say input like reset, and then you'd have like wire reset on a separate line. But you can do that all in one line now. And I'll show you that in the compiler options in the actual Altura tool today, if you remind me if I don't forget. Okay, then I have what I call my local registers, things that I use throughout my module. So here's a list of wires and regs, some local parameters right here. And these I use in my state machine. I like to use names instead of numbers. So here I've declared, and you could declare these one line at a time. You just put a semicolon at the end of each line, or you can list them like this if you want. And they could be, they don't all have to be on separate lines. This is just my style. They could all be on the same line. Notice that the last one has a semicolon in this method with the commas. Okay, so in this particular receiver, now we know that the transmitter is going to delay a certain amount of time, then it's going to send 5 sync bits, which are logic zeros, what I call a logic zero. In other words, you have the rising edge, a pulse here, which is a quarter of the cycle, then 2 cycles are low, and then of course your low cycle for the last quarter. Okay, so we have the 5 quote logic zeros, and then there'll be a low that's greater than 2 bits of time, and then that'll be followed by the data bits, which will be logic ones or quote logic ones or zeros. And of course you could do your own method. This is just a method I chose. So let's go down to the rest of the code here, and in this code you'll see that I have an always block that's running on the positive edge of clock. Okay, that's the only controlling event type statement in this always block, and because of the way I've written it, this is RTL code. This is a subset of the Verilog language that can be synthesized. We'll be talking more about that in the upcoming lectures. So anyway, I have this block. Okay, and you'll notice that within this block I have different variables that I'm creating, and each of these are using non-blocking assignments. So that's the key, that these get turned into flip-flops, this basic structure. Like I said, we're going to cover more of this in the lab. Then the next always block that I have in here, you'll notice I said @ star. I could have a sensitivity list where I list everything, and that would be in accordance with the 1995 Verilog standard. This will work according to the new 2001 standard. As early as last year, though, I did see there was one case I had when I was using the Xilinx tools, the Xilinx ISE tools, that it wouldn't take this for a particular thing that I was doing that had to do with some generate statements, which are part of the new Verilog standard, 2001 standard. And under a certain condition, it wouldn't take this. So I had to revert back to the 95 standard and have a sensitivity list here. But in general, I like using the @ star. It just means that I don't have to list everything, because I may be changing things, you know, as I change my code, and sometimes you forget to put them in your sensitivity list. So this part here, you'll notice there are blocking assignments, okay, and because of the way this is written and structured, these will all get turned into combinational logic, ands and ors and nots and gates, okay. No flip-flops. So how does my state machine work? Well, you'll notice that this part of the code, this second always block, that's combinational logic, everything is based upon the state, this TB underscore state. Okay? And TB state is the output of a set of flip-flops. So let's go back up to my local registers here that I've declared, and here you'll see TB state. It's 3 bits wide, and then I have another reg value that's called TB state next, and that's actually a combinational type output, and I'll show you how that comes into play. But anyway, the way I've written TB state is these become the outputs of 3 flip-flops that hold my current state that I'm in for my state machine. So let's go back down and let's look at, okay, we'll look at the first always block here.
All 2 flip-flops, right?
Excuse me? Say that again?
Two flip-flops up at the top, not 3.
What did I say? Oh, yes, I'm sorry. 2. You're correct.
The definition of TB state.
Yes. Okay, so here we have, yes, 2 flip-flops. And that's because I only need 2 because I only have 3 states. So I could have up to 4 states with 2 bits. So here are my states, idle, bit, and next. Okay? Then let's go down to the actual state. Here's where I declare the flip-flops, basically, right here. Here I have a statement that says if reset, then I force my state to idle on reset. Otherwise, the state is going to be able to whatever this variable is called TB state next. So that's the basic 2 flip-flops there that'll get created. That'll contain the state. So then in the next always block down here, everything in this block is derived off of that TB state, the output of those flip-flops. Okay, so here I've said that if I'm in the idle state, then I wait for this condition, and then I say that my TB state next is equal to this state. So that when the next clock comes, let's say I'm in the idle state, and let's say that this occurs, then this becomes TB bit. So then on the next rising edge of clock, this state value gets clocked in to those flip-flops. And that's how we change state. So then the combinational logic, and this is based on TB state, which is the output of the flip-flops. So TB next is going to be based on this state, TB bit. And so the next state that I'm saying will be based upon the current state plus some of these inputs that I have here, like this resync or this dB rise. And that's what determines which state I'm going to go to next. So that's the basic structure of how this works. So anyway, the way this works is if I'm in idle, I wait for the signal called dB rise before I go to bit. Okay, so what is dB rise? Well, dB rise, excuse me a second. dB rise is just a 1 clock wide pulse that occurs at the rising edge of a data bit or a sync bit. So how do I create that? Well, in our last lecture, well, pre-lecture I guess it was, we talked about how I create a 1 wide pulse based on the rising edge of a signal. And should I go through that again or not? That's what these flip-flops here are. Create the signal called dB rise. Should I run through that or just continue on? So basically this is a 1 clock wide pulse that detects the rising edge of a data bit or sync bit. So in my state machine I says when one of those come along, then my next state will be bit. Okay, and I'll stay in this state based on these equations here. Okay, if I get a what's called a resync, in other words, there was a low time longer than what the bit times are, then I'm going to go back to idle. Otherwise, if I get another dB rise, I'll go to this dB next. I don't know if I want to, I don't know how much of this we want to go into detail or just kind of discuss generically what happens, and kind of actually show. Maybe I should just show you kind of what it actually does in simulation. Would that be of interest at this point?
Sure.
Okay. So let's go in my simulation. I've got a lot of other stuff in my simulation, but I put this in here for now. So let's say I instantiate the one-wire transmit module and the one-wire receive module that we were just looking at. So what is this doing right here? What am I doing by doing this? Anybody have any comment? Okay, well, data bits. Go ahead.
You're waiting for that long.
No, I'm doing an instantiation here. The pound sign in this case means that I'm going to override a parameter. Okay, I'm just instantiating a module. So here's so here's what happens now. Let's go back to our receive, and I said data bits, and I said 16. So what I'm wanting to do is I'm wanting to override this parameter. So instead of it being a module that receives 64 bits, I want it to receive 16. So that's why I call it a parameterized module. So now, let's go back. I'm telling it I want to receive 16 bits. Now in the transmitter, I said, okay, I want to transmit just 16 bits too. So I want to do a similar thing. And there's another parameter I wanted to override, so it didn't take so long. And then this is another parameter I wanted to override it so that it sends out this sequence every 10 kilohertz. And those were parameters that were in the transmit module right here, frame frequency. And so that's why I put these right here at the beginning. And the reason I tend to there's different ways of writing, but the reason I do this method is I list my signals on the module line here, but then I don't actually declare whether they're input or wire yet. And the reason is I want to put my parameters in here because I may actually do some calculations like these local params based on these parameters. Okay, so they need to be after parameter, and then I may actually want to change widths of things based on those parameters. So that's why I want them all before my actual input declaration here. So this is a general format that I use all the time. So let's go back to the simulation file. So I've instantiated the transmitter, and I have it right now. It's going to transmit just a value of 035C just for fun, for 16 bits. Okay, and I take the data out of the transmitter, and I call it OW data, and I run that right back into the receiver, right here, the data in pin. So I'm just physically connecting these two right together, just like wiring them up. Okay, and then there's some other signals like the received data is ready. I can use that elsewhere in the simulation. I'll show you that in a minute. And the actual received data. And then I feed it a clock, my local clock that I'm using, this IF clock. And then reset. Both of them use the same reset. So now, let's say over here I've got to compile it because it's not compiled. So I say compile, compile selected, sim.v. And boom, I get an error. Okay, so I look at my error and I say, oh no, what happened? So I start looking at these comments and it says error, da 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 da. External function, frame frequency may not be used in a constant expression. So I look at that, line 313. So look at line 313. What's wrong with this line? Anybody? Why is it saying external function frame frequency? That's not an external function in my one-wire transmitter. So what's it trying to tell me? And what's wrong with this statement? This instantiation? Well, the problem is I forgot to put dots right here. Very common mistake, so I thought I'd throw that in there. Same thing on this line too. Okay? Because I know this is not a function, so without the dot it thought it was a function. So sometimes it's not easy to understand the errors. I mean, because it's not what you thought it would be. So now let's save this. Save. Now let's try compiling. Compile. Compile selected. Ah, successful. So that was good. We cured all those errors just by doing that. Okay, so now the next thing we want to do is we want to simulate this. I happen to have a script written called sim.do, so I'm just going to do it. And it does the vsim with all the stuff that I need. Okay, so it runs, and it's starting, and it's going and going, and doesn't seem to be stopping. So let's stop it, and let's find out what's going on. So let's look at the simulation, and we see we have a bunch of unknowns on these signals. I'm looking at, these are the signals within the module. Okay, and here's the, in the hierarchy, you can look at your hierarchy. Here's sim, and in sim we have this NWR, if you remember. The, where, sorry, wrong one. OWR and OWX right here. That's the instance name right there, OWX and OWR. You can give it whatever name you like here, because you could instantiate the one-wire transmit or receive. You can instantiate it more than one time, so you can give them different names for each instantiation. So I gave them this name. So within there, if you come over here, and this is in ModelSim that I'm doing this, you can go in your hierarchy, you can click on the particular instantiation like OWR here for the one-wire receive, and here you get a list of all these internal signals and variables that you're using. Okay, so what I did was, in the WAV file, I just clicked on them and then drug them over and added them in here earlier, so you can list the signals that you want to see. So now we have to figure out, well, why am I getting all these unknowns? Well, so let's take a look at some of these signals. First thing you want to look at is, well, do you have a clock and do you have a reset? Well, the key here is my reset is unknown. So now we have to go find out, why is it unknown? So I go back to my simulation. I see, okay, here's my reset right here, and here I've got them both, but let's go look and see where it comes from. Okay, there, I declared it, so I've got it. So, well, I forgot to uncomment my code to do the reset here. That might help. So here in the code, I said, in my test bench, I said OW reset equals 1 tick B1, set it high, delay this number of time units, and then set it back low. So now let's save it, and let's go back to project, then we'll go back, compile, select it, and it compiles again, okay, and then I'll run it again. Okay. Hi, and it finished this time. Okay, and you can see right here where it stopped. It got to a certain thing and then stopped. So now we go back and look at the waveforms, and hey, we've got some stuff this time. I can do a zoom fit. Guess it's already fitted. And we can see here's the transmitter stuff that I have in here. And the transmit data was 035C. And if you look up here in the receiver, you can see that we actually got it. So it worked. Okay. Now we can take a look at, zoom in on a little bit of this. Right here at the beginning, these are the actual sync bits. Remember I talked about the 5 sync bits? So here you can see, let's look in the transmitter. Right here before the first sync bit, you'll actually see, okay, there's the reset. Then after the reset finishes, this delay count starts counting, and it gets up to a certain value. And then what happens? Well, if we go back to our code here, transmit, in the transmitter, remember I have this valued num delay clocks that calculates a certain number of clocks based on the frequency and everything. In my state machine for the transmitter, basically in this state, this OW delay, it waits for that before it advances to the next state, which is OW frame. So let's look at OW delay. That's a state value of 1, and frame is a state value of 2. Let's see, did I put my state in here? Transmit. Maybe I didn't put it in here. Let's so let's put the let's put the state in there right here. Let's stick our state in here right here. Okay, now I'll highlight this window and then do a save because I want it to save it to my current file. Okay, so let's run it again. Okay, so now let's go and look at the, okay, stop. Zoom fit. Now zoom in. And I'm going to change this to radix unsigned, so it'll just be an unsigned decimal value. So here you can see the state changes. Okay, I'm going to zoom in here again. Okay, so there's our reset. Okay, that was generated by the sim.v. If we go back up here, where was that? Right here. I set it high at this is at the beginning of the simulation. Delay a certain amount of time, then set it low. And that's what we see right here. Okay, and when reset goes away, you'll see that the state changed from 0 to 1. And why did it do that? So, well, we go back to our transmitter, and when we're in reset, where's OW state? Here we go. When we're in reset, the state goes to idle, okay? And then it's based upon, then the state becomes OW state next, based upon the state machine. So in the state machine, we're in idle to begin with, and we stay there as long as we're in reset, and then the next state becomes OW delay, and that is a value of 1 right there that I have. And then the next one after that is OW frame, which is a value of 2. So then in the delay one, in state 1, we stay in that state as long as this delay count hasn't reached this value. Okay? Well, delay count on reset, it also gets cleared, and then it just starts counting. Okay? So that's what we see going on right here. So after the reset goes away, it starts counting up. And so it gets to a value up here of 50. And how did it get to 50? Normally it's a lot longer, but in simulation, I overrode that value in my instantiation. Let's go back down. Oops. Okay, right here I said num delay clocks is 50, so I overrode it just so it wouldn't take forever, because normally this would be a very long time. So I overrode it just for test purposes for now, because all I'm doing is just doing testing. Because normally it's going to take like 200 milliseconds. I don't want to wait 200 milliseconds of simulation times. So I said, okay, just 50 clocks instead of, millions of clocks or whatever it takes. So I said 50, and sure enough, that's what we got here, was a value of 50. So as soon as it reached that value, the state machine says, okay, we're going to advance to state 2, which is a little hard to see here, but we'll zoom in. It went to state 2. So then what does it do? Well, in this state, when it gets to OW frame, it merely goes to the next state. Okay, I use this state to actually change some variables. So it just stays in that state for just one clock period. And that's what we see here. Just one clock period. So on the next rising edge, the OW state next, might be interesting to list OW state next so you can kind of see. Let's take a look at OW state next. The only bad thing is I have to. Okay, let's change the radix. Radix unsigned, and then save it. Okay, and then we'll run it again. Okay, let's go back. Zoom in. Okay, let's zoom in here, zoom in down to the very beginning of time, right down to our state 2. So here you can see that, oh, no, let me go back. Here when we're in state 1, my next state is calculated based on the current state. And you can see when the count gets up to 50 that the next state is equal to 2. So when the clock comes along, that's what it clocks in as the 2. Same thing for the 3. When I'm in state 2, I said that OW state next is equal to 3. And so it clocks in the 3 on the next rising edge of pause edge clock. So that's how the flip-flops work. I think we're nearing time for our lecture. We can kind of come back to this again. And let's see here. Anyway, so that's the delay count, and I shortened it like I showed you just so that we wouldn't have to wait a long simulation time before the actual bits started. But let's take a look. You can kind of see these are the logic zeros that I send out. It does 5 of those. Then there's another delay time, and then the actual data bits start. Okay, and in this case there's 16 of them between here and here. And there's a logic 0, logic 0, logic 1, logic 1. Okay, and there's my little dB rise signal based on the rising edge of this data in signal that I created. So you can see that it's created once every bit. That's what I wanted. Okay, and then after 16 of those, it grabs them all. You can look in the code, and it's putting out the least significant bit first, so you have to read this kind of backwards. 0011, that's the C of this 035C. It's all going out least significant bit first, and then 1010, that's the 5, etc. So there's actually a lot of stuff that you can look at doing this. Okay, any questions before we start on with our lecture for today? Anybody have any questions? If not, I guess we'll go on. Can you hear me okay, Michael?
Yeah, it's all working fine.
Okay.
Yeah, we can hear you.
All right, just want to make sure everything was very quiet. Sometimes I just think I'm talking to myself. Okay, so we're going to begin looking at synthesis technology now. And I've got to get this going here. Okay, so let's take a look now at synthesis. Here we have a typical HDL, hardware top-down flow. And here we've written our HDL, hardware design language descriptions, and we've either written them in behavioral models or RTL, maybe we've written test benches, and we want to actually run those through some sort of verification simulation like I was showing you just now. And if we find problems and we want to go back and we want to debug that and then simulate again and keep doing that, and that's what we call our functional debug. Then after we've gotten that working, then we're going to actually want to synthesize this stuff and produce some real gates. Well, after we've synthesized it, we may want to take that gate level definition and actually run that back through verification too to see that, hey, the gates that it produced is still passing our functional verification tests. And then let's say that works. Once you finish that, then you're probably going to want to do some timing analysis. The tools such as Altera's ISE tools and Xilinx's ISE tools and Altera's Quartus tools, they have built-in timing analysis tools, and you're going to want to use those to see that your design meets timing analysis. Then you're probably going to want to do some more testing. If you're doing an FPGA or an ASIC, you're going to do this. If you're doing maybe if you're doing an FPGA, you'll be doing this a lot. If you're doing an ASIC, you may have to go through some layout tools, and eventually you're going to ship this thing off. And then you're going to have to test it when it comes back if it's an ASIC. So let's look at the actual synthesis process, where you take your HDL description and synthesize it. So you start off with your HDL code, Verilog code. You're going to compile it with your tools, and that's going to produce an intermediate set of Boolean equations and state elements. And then it's going to run through a mapping process typically, where it's going to include things such as your target library, which your target library, let's say you're using Altera, it's going to be the target library for that particular Altera device. So you might be thinking, well, what do they have in the target library? Well, let's say that in your equations, let's say you had a function that required an 8-input AND gate. And let's say that, you know, the physical FPGA doesn't have an 8-input AND gate. Okay, well, this target library, it would know things about, it would know that, oh, all I have, the maximum I have is like a 6-input AND gate. So it would take, you know, a couple of AND gates and build an 8-input AND gate based on the target library. So the target library is a real physical thing that we're going to want to produce too. And then there's also going to be inputs into this mapping, such as things of like whether you want to do some optimizations on area, power, and speed. And there's a lot of those things that the Quartus tools have. That's something that we could take a look at sometime, so you can see all the different optimizations that you can use. And it'll run through the mapping, and then that might produce a network of cells, and then that might, after that, typically you might make a net list. And finally you get down to this net list that has all of these vendor type library gates in it, and then they're all connected together. So it's just like a sea of gates and stuff all tied together. Okay. There's also different levels of abstraction. We've talked about behavioral models. These are functional models where you can use the whole Verilog language. Then there's the register transfer level. Okay, and that's where you actually implement the model. But you're only implementing it, you can only use a subset of the Verilog language. But this is the level that you can actually synthesize. You can't synthesize this, but this is very useful for simulation purposes, and maybe just to create a functional model to begin with, to see that, you know, to test other models with real quick before you actually have the RTL code written. And eventually, after the RTL, you're going to get a gate implementation. It's going to produce real physical gates, ands and ors and flip-flops and latches and all those type of things. So in this RTL synthesis, you're going to have inputs and outputs. You know, you're going to have default things like optimizations and libraries and different input variables that you can send into it for compiling, constraints, maybe scripts, so a bunch of control logic that can go, a bunch of control information that can go into synthesis, along with your RTL code, along with your libraries such as vendor specific or generic. They might include things such as wire loads in them. Also, you may be using IP cores from some database that the manufacturer of the tools has. So like Altera has what they call mega functions you can use. You can incorporate those. You don't actually have to write the RTL for it. And then after synthesis, you're going to get things like log files and reports and net lists. Okay, so you can look at these reports to get ideas about what happened during your synthesis process. So now we're going to begin looking at RTL coding for synthesis. So there's basically three types of building blocks for RTL models: combinational, combinational with latches, and flip-flops plus combinational. So these are the notation. And of course you can mix and match these how you want. So yes, I could have combinational after this flip-flop. I could add that after it. Okay, let's talk about describing combinational circuits. In combinational circuits, the outputs are a function of the inputs, and the outputs should update automatically when the inputs change. And so there's no storage elements like flip-flops. And you can describe these in different ways. So here's the description we have of this module called design. And we have a output data, and data right here is a 4-bit wide register. Now this is, again, I'll just mention, this is compatible with the 1995 version of Verilog. And the newer 2001, you can put this reg right here after output, so you wouldn't have to have two separate lines. So here we have an output, 4 bits wide, and we have a wire that we're using in this module called VAL, and another wire called read. And here we have an always block, so anytime that val or read change, it goes through this always block. And then data is based upon these two inputs here, val and read. So if read is true, data becomes val. Otherwise, data becomes tri-state. Okay, so this format would describe purely combinational logic. Okay, notice that we use the blocking assignment, the equal sign. So always block must be sensitive to all the inputs. Okay, so, and that's the only way that you can guarantee equivalence with a simulation. So let's go back. In this case, our sensitivity list here is the val or read. Okay, those are the two things that we use inside of here. And you will get a warning if one of them's missing. I don't think I've ever seen it not give you a warning. At least you get a warning. Okay, so this is our sensitivity list. So we need to put all of them in there. And the key to making this combinatorial logic is there can be no further event waiting type statements in here. This is the only one that you would have. The rest of everything inside is just purely assignments like we had here. Okay, there's no wait statements, no delay things, you know, just pure. Okay, let's go to the next thing here. Here's another example. Here we have another always, and our sensitivity list has A or B or C. Well, C is oh, yeah. So here we have A, B, and C. Now output doesn't have to be on the sensitivity list. This O doesn't have to be on the sensitivity list since it's an output. And temp, because temp is assigned before we actually read it right here, it can be, it's an intermediate value, so it doesn't have to be on the sensitivity list either in this case. So I like the newer notation. You just put @ star, and you don't have to put any of this mess. My personal preference. But I'm going to show you this in case you ever run into a problem and you have to list them for some reason. Here in this example, we've put C on the sensitivity list. Maybe we were using it in the code and then we got rid of it, and so it's not used anymore. And it just might slow your simulation a little bit or something, but that's another reason why I don't care to use the sensitivity list if I don't have to. Here we've said output 1 is equal to A plus B and output 2 is equal to A plus D. Now the problem here is we're going to get a warning because we didn't put the D on the sensitivity list. Okay, here's another method you can use for doing combinational logic. You can use the assign statement. So you just say assign data equals, and then based on read, either value or the tri-state. So for simple things like that, that's much better. You can also do things where you instantiate the primitives. And here we've instantiated these buff-if-ones, 4 of them. That's the instance name for them. And that does the same equivalent thing, and that too is acceptable. So that's kind of like doing schematic capture where you're plunking down the parts and connecting them up. These are some guidelines. It's up to you how you do it, but I'd say avoid using primitives unless you have to use them. And use continuous assignment for simple expressions. It's more readable that way. And the preference is that you should use always blocks, especially if you're doing things like state machines, finite state machines, like I was showing you before the lecture. And initial blocks are illegal. So you're going to use always blocks, but you cannot use the initial blocks. Thing for you to think about would be, how would you even implement them? Because what's different about them? Well, they execute once and they stop. Well, flip-flops don't stop. Neither do combinational logic. So anyway, it's not part of the RTL code. You can't use them for RTL code. I'll talk a little bit about the labs you're going to be doing for this lecture. There's a completed self-checking test bench provided for each of the labs. And I want you to make sure that your RTL description passes the test bench before you attempt to synthesize. And the garbage in, garbage out principle applies much more when you're trying to actually produce hardware. And you're going to have to learn how to use your particular synthesis tool. So try to find a tutorial. The ModelSim, should be an online tutorial that you can look at and read, or just start practicing with it. But that's something that you're going to have to learn, is how to use your particular synthesis tool, because all of you out there have different ones, I know. So in lab 9.1, you're going to complete the description of a simple combinational function and become familiarized with the synthesis tool. And these are the labs. You'll have this information in your lab. Repeat it again. Functionality. Okay, here are the...
Hey, Kirk, I have a question.
Yes. Go ahead.
Does ModelSim have a way of checking that your RTL works?
ModelSim have a way of checking. Well, that's up for you to write in your Verilog test bench. So, like in the example before the lecture, yeah, you're going to have to write some sort of test bench, and then you'll compile that code along with your real RTL code. Like in my case, the real RTL code was the one-wire transmit, the one-wire receive, and then I have a test bench that actually, drives that. And there wasn't very much in what I showed you as far as driving it. It just had it run a little ways and stop, so I could look at the signals. But you could have it check. You could actually, in your test bench, you could say, after it goes a certain amount of time, you might want to test the read values, make sure you're getting back the right read values, and if it's not, you print out some statement. Okay, you might want.
Is there a way with ModelSim to check to see that you're not using initial blocks?
It's going to tell you.
That are not.
It should warn you. In that case.
Oh, so there is a warning mechanism at least in ModelSim.
Yeah, there'll be a warning mechanism there. Yeah, it'll tell you basic things that it can't synthesize. Well, no, I'm sorry, not in ModelSim. It's not actually. I'm sorry. I was thinking of the vendor tools.
Okay, that's what I was wondering.
Yeah, ModelSim doesn't care whether you're doing the full functional Verilog or just the subset. It doesn't know what you're up to. Sorry, my brain was on a different. My brain was on a different page there for a minute. Yeah, but when you go to synthesis with your vendor tools, whether it be Altair or Xilinx or whoever, then you're gonna know whether it's synthesizable or not. You're gonna get warnings.
Okay, great, thanks.
Okay, so here's the allowed operators, which are most of the operators. There are a few that aren't used, but here we have arithmetic operators. There are some limitations on the multiply and divide and modulus, but you can use plus and minus and all of these. You can use the bitwise, the logical, relational, etc. All of these different type of operators you can use in your RTL code. Okay, you can't use the identical operators, if you remember those. Okay, and just arbitrary multiplication is not allowed by all synthesis tools because it requires a full combinational multiplier. So you're going to have some limits if you're trying to do multiply and divide also. You might be limited on the multiply and divide. Other statements that are allowed are the if statements, the case statements, and the for loop statements. For the for loop, you can just do simple iterations only, and the body of the for loop is replicated for each iteration. I'll show you more of that later. You can use functions. The body is expanded inline, but you cannot make assignments to registers outside of the function. And for tasks, if you're using those, also the body is expanded inline, and you cannot make assignments to registers outside of the task, and you cannot have event type wait statements in the task. No wait statements, or at something within the task. So there are some limitations there. So here we can look at the if statement. You can use this in your RTL code. So here's an example. Said if odd equals 1, parity equals this, otherwise parity equals that. So you can use the if else. You cannot use the identity operator, so be careful there. Only the equal, equal, or not equal. The if-else, if combinations generate priority encoders, like this here. Uses separate if statements for mutually exclusive expressions that assign values to different variables. So here we have if a equals 1, we do this. Else if b equals 1, we do this. Well, in this case, you notice that I have O1 equal to C, and I have O2 equal to D. Well, these are mutually exclusive, so you should rewrite this differently. You should just say if a equals 1, output equals C, because that's what we want. And in this case, because we did an else if b equals 1 tick b1, what we're really wanting here is if it's a is equal to 0 and b is equal to 1, then we want output 2 equal to d. So we should write these as two separate if statements. So try not to be doing this type of thing when you write your if statements. And do them like that. Do them separately. Sequential assignments to the same variable create priority encoder. So here you see that I said if a equals 1, output equals d, and if b equals 1, output equals c. Okay? So it actually, when you write it like this, it actually produces this, but I prefer that you do this and not this. But be aware that you can do this. Okay? You should use a case statement for mutually exclusive expressions that assign a value to the same variable. In case statement, you can use case statements, and usually the case statements are what we call parallel, and that means that each case is mutually exclusive. So if you look at this particular case statement, here we have 2, 3, and 4. Each of those are mutually exclusive. Then we do something. Okay. And same thing here with this case X. These are mutually exclusive. They don't overlap. But what happens is if you do something that's not mutually exclusive in case statements, such as this one here, where they overlap, then it's actually turned into a priority encoder when the case statements overlap. So it would look like this. This would be a priority encoder. It would take this one first. So if the opcode is equal to 4 tick B0000, then you do whatever, this here. Else, if opcode of 2:0, that's these 3 bits right here, these lower 3 bits, it compares that to being 0 and then does whatever you want it to do. So that's how it's going to do it if it's not a quote parallel case. It's where they overlap. So be aware of that. Or it can also do it if you if you have case items that are expressions. So like in this case I said case, I put a value here, and then the case statements are actually like the variable a and b. So this gets turned into if a equals 2 tick b11, that's what this is doing. Then you do something else. If b equals 2 tick b11, then you do this. Okay, so this is the equivalent of that. And the synthesized logic, of course, then for this is here a is equal to 11. Doesn't matter what b is. You get this particular output here. However, if A is not 1, 1, so it'd be like 0 something or something 0, then if B is 1, 1, then you get these outputs. So this is the equivalent structure of this. You can, in some synthesis tools, you can declare case statements to be the quote parallel case statements so that they're mutually exclusive. But it's tool specific, and there's a lot of the tools will recognize the synopsis directives. Synopsis has directives that you can embed in comment lines. And what they do is you put your comment line, then synopsis, and then there's some information you put after it, like in this case parallel case. So we're telling it that, like if you're using the synopsis tools, you're telling it that, hey, these are going to be mutually exclusive. I want you to generate your logic as though these two things are mutually exclusive. Okay, and then it would actually produce mutually exclusive type code. So the thing to be aware of here is if A and B really aren't mutually exclusive, then what's going to happen to your gate level in simulation? Something I want you to think about. I want you to maybe test it and try it. But you can do this. You can declare that they're mutually exclusive by using a directive. And a lot of tools, not just Synopsys, will actually recognize some of these things, but you need to know based on your tool. I'm not familiar with the Altera ones enough to know what it does. I haven't tried it yet. Haven't needed to. Okay, so in this case, instead of...
Are these compiler directives?
Yes, these are compiler directives, synthesis directives.
Compiler directives?
Huh?
Are they always on comments?
No.
Are the compiler directives?
No, these are special things.
Comments?
These are special things that some vendors have come up with, embedded in comments. It's not part of the Verilog language. It's something that, you know, Synopsys started doing this. A lot of people kind of followed after them. So it's vendor specific to the tool. So I just want you to be aware of it in case you see it or think you have to use it for some reason. Okay, first of all, your tool would have to be able to support it. Okay, that's why I say here that it's tool specific. So in this case, because of this, if this were the Synopsys compiler or one that was compatible with it, then if A is equal to 2-tick B11, then the output would be whatever this is. And then for B, it wouldn't be that if else. It would just, you know, if B is equal to 1, 1, then you'll get the output. It doesn't care what A is. Whereas in the previous example here, it does matter. Anyway, I just want you to be aware of this. Sequential statements. The inherent behavior of sequential code is maintained. Using a previously computed value references its intermediate value. I'm going to show you that in just a second. Overriding a previously computed value takes precedence. So here we have an example. We've written an always block, and whenever these two items change, it's going to go through the always block, of course. Here we started off, we said that parity is equal to the exclusive OR of the data. Okay, so that would be all. This is a bitwise exclusive OR of all the data bits, however wide this thing is. And I said if odd equals true, then parity gets set to the not of parity. Oh, like I said, you can use the for loop statements, and the bounds must be known at compile time, and it can be things such as parameters. Remember I showed you parameters or local param. You can define values, or you can put constants right in here as long as you're using constants. Okay, so the loop can say for I equals some value to some other value, basically. So you can use your greater than or less thans, all those different type of things to get to your destination of the loop. And then you have these statements. So let's look at how we can use it to write generic code, because it replicates the body, and this is the body right here, with each iteration. So here I've written a for loop, and I said I equals 0, and while I is less than 4, I equals I plus 1. Okay, so in the body of the for loop, I've created my logic. I said O of I, so I'm using this index, is equal to I of I ANDed with M of 3 minus I. Okay, so it's going to replicate this for each loop iteration. So it's going to be equivalent to these four statements, where you have O of 0 equals to I of 0, ANDed with M of 3, etc. So it actually replicates your logic that you're wanting to produce. So here's another example of doing that, how it can be used. One way that you could use it. You can use or recompute previously computed values. So here we start off, I said parity equals 1 tick B0. And then I said for I equals 0 to less than 4, same type of loop. I'm going to do this 4 times. I say parity equals parity exclusive ORed with I. So here's what happens. On the first iteration, we would get this. Parity equals parity, which is 0, exclusive ORed with I of 0. And then this of course will get optimized, because anything exclusive ORed with 0 becomes that value. So anyway, this is the output from your first iteration right here. Then that for the next loop is actually going to get used in the second loop. Okay, and then you get, that's your second iteration, what you'll get, third iteration, and then finally your fourth iteration. So this is not the way I do parity, but I mean this is just an example of how you can use the for loop. Now if you use expressions in vectory and memory indexes, it's going to yield multiplexers. So here I have a, let's say I have a 4-bit input called I, and a 2-bit input called S for select, and an output called O. And I say assign O equals I of S. And you can do this. And so these 2 bits will select one of the 4 bits of the input by doing this. So here you can have S is 0, then it would select the 0th one of I. If S is 3, 1, 1, then it'll select the I of 3 for the output. So you can do that type of thing. That's synthesizable. Here's another thing, another example that's synthesizable. Here I have a little register called reg file. It's 8 bits wide and it's 8 deep. Okay, so it's like having 8 memory locations, 8 bits wide. Then I have a variable called op, and it's 6 bits wide. And I said always that op or reg file. So anytime anything in the register file changes, or this variable, reg file, or anytime this variable, op, anytime it changes, we come into here. And the output then, I said, is based upon this function. So I said reg file of the upper 3 bits of op. Okay, so if I've got 3 bits, I can select one of 8 locations, right? Okay, so these 3 bits allow me to select 8 locations. Well, that's what I have. I have 8 locations in this reg file. So that's what this is doing. So this value here, op5:3, is going to go from 0 to 7. Well, and that's what we want, 0 to 7. We're picking a particular one, and then we're adding it to another one. Okay, and the lower 3 bits of op, this value here is going to go from 0 to 7, can be 0 to 7. Okay, so we're picking another location in reg file, and then we're adding those two together. So that's synthesizable. You can do things like that. So in Lab 9.2, you're going to complete the description of a simple combinational function, and these are the files you're going to find in the lab directory, but you'll have lab instructions for this. And in the Lab 9.3, you're going to describe a complex combinational logic circuit using abstract statements. And then you're going to have a couple files for that. Latch inference. Now, timing analysis tools, such as the Altera Quartus tools, are designed to work with synchronous flip-flop controlled circuits. And synthesis tools do not generate glitch-free logic. That's going to be up to you to realize what you're doing. Okay, what do I mean by glitch-free logic? Well, let's say that I had a flip-flop, and for the clock, it didn't just come from a particular clock source, but it came from some combinational of, maybe a couple sources. Okay, you can get into a real problem here, and this is what's called a gated clock. You can have bad problems. What can happen is when it's switching from one condition to another, you can actually get a glitch here, a sharp narrow spike that's on this signal. And when you do that, you can violate things such as setup and hold times, and you can cause the flip-flop to go metastable. You can really screw things up. So you better be sure of what you're doing when you have gate-controlled logic, because it may not be glitch-free. Okay, designs containing latches are not suitable for static timing analysis. Okay, when I say latches, I'm not talking about flip-flops, I'm talking about latches. And they're not suitable for scan-based testing and race-free conditions. So stick to combinational and flip-flops. Latches, you're going to need to know what you're doing there. They're just problems. So latches are inferred when under some conditions a register is not fully assigned in an always block. And so what happens is the register maintains its previous state. Here's an example. The register is not assigned in all branches of the if statement. So here I've said if enable equal 1, O equal I. Well, here I'm using the blocking statement, the equal sign. It's different for the non-blocking. If you're using this and you don't describe all of the conditions for it, then you may infer a latch. Now your tool will tell you if you've inferred latches, and you need to look at that very carefully and determine what you were really trying to do. Were you trying to create a flip-flop, or were you trying to produce combinational latches? Do you really want a latch? Here's another example where the case statement is not fully specified. So here we've got enable. If it's 1, we said output to I, but if enable is 0, we don't do anything. So it just kind of, see here we've said every time enable changes or I changes, we come into here. So this actually produces a latch, since we didn't fully describe everything. So here's another example where the register is not assigned in all cases of a case statement. Here we've said for enable equal 1, output 1 equals I, and for enable equals 0, output 2 equals I. Well, these are two different outputs that we're doing here. So output 1 is not defined for this case, and output 2 is not defined for this case. So when you get something, when you run it through your synthesis tool and you see warnings that say you've inferred latches, go back and look real carefully at your code. Okay, so the guideline is don't use latches. Okay, you're going to get good timing analysis if you don't use them. Otherwise, you're going to have problems. And it's also easier to use scan and formal verification techniques. To guarantee no latches will be inferred, provide default values for all outputs. Okay, so this would be the best approach. Remember, I could say here output equals 1 tick B0. So this, at least this guarantees that output is going to get assigned some value, and then I might have my other if statements. So that's one way to get around that problem. Just be sure that you specify the value under all conditions. So that would be all the branches in the if statements, all the cases in the case statements, and use a directive to specify case statement as full if you need to. You can also put a default statement in. I didn't put that here. I should have done that. You could put your default statement in and make sure it gets a particular value. And just keep in mind that the simulation may differ from RTL to gate if the case was not a full case statement. Okay. Let's talk about don't care things, like when you want to assign a tick BX when the value is irrelevant. And those will get optimized to 0 or 1 by the synthesizer. And so it'll yield a smaller and faster implementation if you do this. But remember, you'll get a difference between the RTL and the gates, but it won't matter because if they truly are X's, then you don't care what it produces for that particular case. So here's an example. I've got a 4-bit register called BCD. Anytime that changes, I'm going to say if BCD is greater than 9, then this other output thing that I'm creating here, I'm going to say it's equal to 4-tick BX. I don't care. I'm only interested in stuff from 0 to 9. Okay? So when it's from 0 to 9, bin is going to be equal to BCD. If it's something greater than 9, I don't care. So in simulation, you're going to see 4-tick BX. But in the actual gate level, if you were to simulate the gate level after it's synthesized, you're not going to see X's. You're going to actually see different values of 1s and 0s, whatever the synthesis tool came up with. And it's going to come up with, different values based on the best optimization it can do for this code. So there'll be real 1s and 0s, but you won't really care since it's greater than 9. Okay? But if you can, assign the tick BX if it truly is a don't care and you don't care what it comes up with for the real logic. This is a guideline you might think about if you want. If you must use latches, you might want to use a distinctive name for the signals that represent the latches, such as maybe you want to put an underscore LT. So that's just a little reminder that, yeah, I really did want to infer a latch here. Okay, so it might help you in your documentation or if somebody else is coming along and reading it. So in Lab 9.4, you're going to learn how to avoid inferring latches and deal with incomplete specifications. Tri-state inference. You can use the tri-state primitives, such as the buff_f0 and the buff_f1, the not_f0 and the not_f1. Okay, you can instantiate those, but the thing about these is they're only 1 bit wide. So if you got something that you need like a bus, you're going to need multiple bits. Okay, so you need a way to handle multiple bit widths. So you could do it this way instead. So like we have a 16-bit bus we want to tri-state under certain conditions, and you could just write the code like this. So if enable is high, then the output is equal to the input. Otherwise, if enable is low, the output gets turned into tri-state. And this way you can handle any bit width. Here's another example of a here we have these 3 things like reg file, adder, and chip select, active low chip select. So here I've gone ahead, I've just assigned data equal to tick BZ, but then I said if the chip select is low, then I'm going to assign data equal to reg file of address. Okay, so that would do a similar type thing. It's another method that you could use. So in Lab 9.5, you're going to learn how to infer tri-state devices, and you'll differentiate between multiplexers and internal buses. And how are we doing on time, Michael?
We have 20 minutes. So
okay. I think I'll go ahead and start then. Here I've got a few more slides. I'll go a little bit further today in the lecture. Let's talk about describing synchronous circuits. And a synchronous circuit is where the state changes synchronously with a clock. And the state may be reset asynchronously if you want to, but there's a limited description for this style. Okay, it's a subset of the Verilog language. Okay, so to do this, you want to be able to infer flip-flops, and the way we infer flip-flops is we use an always block, and it has to be sensitive to the rising or falling edge of the clock. And we must assign flip-flop output using a non-blocking assignment, not the equal, but this notation right here, non-blocking. Okay, and here's our either pause edge clock or neg edge clock. So this type of statement is what describes a flip-flop. So when I say QFF equals D, the QFF is this flip-flop's output. Okay, here I've said always at neg edge clock, and this little bubble just means that it's an inversion or whatever. But your vendor, when you synthesize, typically they have flip-flops that can do both. Probably the most common is the pause edge clock. So all registers assign using non-blocking assignments and for flip-flops, and they use the same clock edge. Here we have an example of QFF being 4 bits wide. Remember in my example before the lecture, I had a state machine that I was writing, and it was 2 bits wide. So here's the way we do this. So always at pause edge clock, that's this. We set QFF equal to D. So since QFF is 4 bits wide, this is what we get here. This D would be 4 bits wide here too. I didn't write that in the notation here, but this would be 4 bits wide, and then each bit would go to a flip-flop, and this is 4 bits wide on the output. So that's 4 flip-flop, and here I said flag is equal to the not of flag. If I do that, then I've basically taken the Q bar output and fed it back to the D input, and I get my flag. So I just inverts the flag on every clock edge, rising clock edge. Okay, one thing you're going to want to be able to do is reset some of your flip-flops and stuff to a known condition, say on power up. So you're going to have maybe a reset. So in this logic, I've used the at pause edge clock, and I'm using non-blocking assignments, so this is going to generate a flip-flop. But I said if SR equals 1, then Q flip-flop gets set, the output gets set to 0, otherwise the Q flip-flop gets set to D. So here's the equivalent of what it would produce. So here we have if SR is 1, it gets it, that's what the bubble means, is an inversion. So then this input to the AND becomes 0, so anything so the output is then 0, so that it gets on the clock edge, it gets clocked to 0. So that's what this does. Otherwise, if SR is 0, then the D will get clocked through. Okay, and some vendors have some vendors have a built-in synchronous reset that you can use instead of putting it inline. Because you notice one of the things here is if you do a lot of this if reset, it's going to put more delays in your logic. It's going to take more gates that way. Whereas if they have a built-in synchronous reset, you're not going to have any delays here. So let's look at an asynchronous reset, and that's where the active edge of it excuse me, my throat is getting dry again. Let me get a drink of water here real quick. Asynchronous reset. The active edge of asynchronous reset added to the, we have to add that to the sensitivity list. So here in the sensitivity list, I still have the at pause edge clock or pause edge asynchronous reset. Okay. Then in the code here I have if asynchronous asynchronous reset is 1, I set the flip-flop to 0, otherwise it clocks the D. So in this case, you're going to need a target library that supports the asynchronous flip-flops. You can do this. Be very careful with asynchronous resets. You can violate setup and holds. Maybe I should post a good paper that somebody wrote on this. What can happen is when you release the asynchronous reset with respect to the clock, you can violate hold conditions, and that would produce problems on your output. I probably need to put up a paper for you to read about that. Here we have a active high asynchronous reset or an active low, and the way we do that is you can use pos edge AR or neg edge AR with your logic here. Okay, so you can use active high or active low that way. Asynchronous set and reset. You can have both asynchronous set and reset. And here's an example. Here we have the pos edge of clock, and here we have our pos edge of asynchronous reset and the pos edge of the asynchronous set. And our code, we said if the asynchronous reset is 1, we set it to 0. Else, if the asynchronous set is equal to 1, we set it to 1. Otherwise, it gets the value of D. Now notice in this case that the asynchronous reset has priority over the asynchronous set. Okay. However, big warning here in doing this. It doesn't accurately model an asynchronous set, reset, flip-flop. Avoid these. Okay, and I'm going to show you why. Let's see here if I get a piece of paper. Let me actually draw some of the... let's take a look at what happens here. Let's say that our asynchronous reset goes high, like we have right here. Okay, so the Q flip-flop gets set to 0. Okay, right here. It immediately goes to 0. Okay. Now, see, am I missing something here? Wait a minute. Oh, okay. Now let's say that while this asynchronous reset is high, we get an asynchronous set comes along. Let's say it comes along right in here. Okay. Now, the asynchronous reset, according to this, is going to still keep it low because it has priority. But now we get to this point right here, when we release it, it goes back low, and our synchronous reset is high at this point. I mean, our asynchronous set is high still. What's going to happen? Okay, when asynchronous reset goes low, it's going to come back into this always block, and it's going to look and it says, is AR equal to 1? No. If this is set to 1, and it is, it's going to set it. Wait a minute, I'm missing something here. Give me a minute to think of what I'm doing. I lost my train of thought. Yeah, that goes. Oh, yeah, here's the problem. Okay. We come along. Let's start over. I'll do this again. Let's say our Q flip-flop is high, and we come along, and on the positive edge of the asynchronous reset, we want to clear the Q flip-flop. And we do that because we have a pos edge of AR. Okay, so we come in, that triggers this to come in again, and we say, is AR equal to 1? It is, so we set the Q flip-flop to 0, and that's what we see right here. Now, it's active, and it's still high. Okay, so the Q flip-flop stays at 0. So let's say while though this asynchronous reset is high, we have an asynchronous set comes along, and it goes high during this time that this is high. So it goes high. Now, when it goes high, that's the positive edge of ST. It comes in here. But we've said that the asynchronous reset, if it's 1, then it just keeps it low. So nothing actually changes. The Q flip-flop still stays low. So now the set is high, and we decide to release the asynchronous reset. What happens then? Well, this is only based on the positive edge of the asynchronous reset, so it doesn't come back through here. Okay, even though the set is high. So in a real flip-flop, asynchronous set reset flip-flop, because this is high, it's going to force QFF to come back high. But in this model, it can't do that because of the way it's written. So it doesn't accurately simulate it for this type of condition where you've got the set changing during the time the asynchronous reset is high. So be very careful of this. Okay, so here's another example to think about why this doesn't correctly model an asynchronous reset flip-flop. So in this case, we've said, okay, well, on either edge. Okay, so now let's actually, I think this is, I think what I'll do, maybe I'll draw it out for you. Yeah, just a minute. Okay, so here we've said, okay, at the positive edge of a clock, okay, we're doing our non-blocking assignment, so it's going to be a flip-flop. We've said on either edge of the asynchronous reset. Okay, so we come along, if it's high, then we set the flip-flop to 0. Otherwise, we check to see if the clock is high, and we set the Q flip-flop to D. Okay, so let's look at the problem here. The answer to it is if the asynchronous reset is low, or while the clock is 1, then the Q will change if D has changed. Let's look at how this is actually done. I'm going to get out of my thing here and see if I can actually get I need something to draw with. I can use paint or something. Paint. Okay, so let me draw this. I'll just kind of crude drawing here. And maybe what I should do is see if I can copy this code here. Can we? Not too good, but get the idea, I think, here. Okay, now let's see if I can do this. Draw a picture. Let's say that my asynchronous reset does something like go like this. Okay, and let's say my D input of the flip-flop starts off low and then it goes high, and let's say it stays high, and then my Q okay. So let's look what happens. Before this asynchronous reset comes along, you can see that each rising edge of the clock right here is going to put the output low. So this will be low. Okay. Now when we get to this rising edge, we're going to get, it's going to go high, right? Because the data input's high. Okay. Now, here the asynchronous reset comes along, it changes high. So we would come into this because it changes on either edge of the asynchronous reset. We said if asynchronous reset is 1, which it is, then we force the output to low. Okay, so this is going to cause this to occur, right? Okay, so now our next event is going to be at the pause edge of this next clock. Okay, as the clock change. So we look, we come in here, and we look to see if, oh, asynchronous reset is equal to 1. It is, so we continue to stay low. Okay, so we're low. Then our next event is right here. Okay, and so we come back into this because AR changed. So is AR equal to 1? Oh, no, it's 0 now. So we go down here and we say if the clock is high, set the Q flip-flop to the D. Uh-oh. So we just went high. So what's the problem with that? Well, the problem is that doesn't accurately model the flip-flop because it doesn't clock based on this going low. It shouldn't set the Q flip-flop back high. It should only do it on the next clock edge. So in real life, this should stay low until we get our next clock edge. And this is where it should go high. So it doesn't accurately model. This is one case of it. It can't accurately model. So be very careful in what you're writing. So let's go back up, PowerPoint. So in the case you just saw, if the AR transitions to a low while the clock is high, the Q output will change if the D is changed, and that's what we saw happen here. So AR went low while the clock was high. Now if AR had gone low over here, then we would have been okay. The problem was during the clock being high. So it doesn't accurately model. Okay, so don't do that. So in Lab 9.6, you're going to learn how to infer flip-flops and to control the number of flip-flops that get inferred. Okay, that's all of today's lecture. We're going to talk more about synchronous logic and state machines in our next lecture. So we could go back. Do we still have a little time, Michael?
Yeah, I can do another 5 minutes or so.
Okay. Let's see if there's anything I can talk about. Well, let me open it up to questions, I guess. We covered a bit of material today. You're probably going to want to go back through this. And also start looking at these, you know, for example, look at the one-wire transmit and receive, so you can see how the state machine stuff was done in there. You can see how the combinational logic was done versus how the flip-flop logic was done. Look at those two always blocks in there. And that'll give you a good example of how to write RTL code. One thing I could point out here real quick is in the Quartus tools, remember I talked about when you synthesize stuff, here I went through compile the design, you can click on this and you can tell it to start or start again if you already compiled. And The compiler, there's different options that you can feed this thing. In the assignments settings, let's see if we can look at some of these real quick. Like here's some under analysis and synthesis settings. There's some optimization techniques, such as it can try and optimize for speed or area or a balanced in between. Just because you pick balanced, just because you pick speed doesn't mean it's always going to give you the fastest one. Sometimes the balanced one will actually give you a better speed. So these are things that you can play with because it'll use different techniques for synthesizing. And then there's other options in here, such as you can set some clock settings. You can tell it what the maximum speed of certain clocks is, so that when it does timing analysis, it'll know whether it meets timing based on those clock speeds. And there's just a bunch of options in here that you can play with. And we'll have to play with those some more when we get into some of this HPSDR code. So anybody have any questions? Or did everybody get lost today? Did I lose everybody?
Hey, Kurt.
Yes.
Yeah, I was muted for some reason. I finally got unmuted. My question was procedurally on the one-wire code that's up on the Verilog APRSDR.org. Should we be downloading that each week, or does that stay the same?
I just put it up there for examples. Eventually I'm making changes, and I'm actually creating another one that I may wind up using. It's called InWire, and it was just there for an example for you to look at.
Okay, I assume that. Thank you. I've enjoyed it so far.
Yeah, eventually I'll post some of this stuff when I get everything working. I'm working on some new stuff right now.
Is this the code that you're working on? Is this in Subversion or CVS?
No, just on my computer right now.